Hi everyone, I hope you are all awake after lunch, so it's going to be a bit comical. Maybe I'll try to make it more funny than usual to keep you awake. My name is Korland. I'm the CTO of incubation in Redis Labs, which is kind of a fancy name to running the models group. My group is running most of the models that you probably saw during the keynotes and you're probably going to see during the conference, like Redis Search, Redis Graph, Redis JSON, Redis TimeSeries, and many more, Redis AI, and Redis gills that we're going to present during this conference a couple of times. So what are we going to do today? So as you saw from my title, the title is about from key value to multi-model and how we see it at Redis Lab, how we want to make Redis to be the multi-model database that we think it can be, and how we envision people using multi-model databases, and not really need to think in advance about what the organization will need 2 years or 3 years from now, but let the database grow with them, go with their needs. So I'll start with some historical coverage about the evolution of databases, and then we'll go through the multi-databases mess, like how people are doing it today. And I hope I'll convince you by number 3 that multi-model database is the right way to go. So the evolution of databases. So it started somehow when the computer started, but officially that coin was termed in the 60s. And it started with like a navigational database, network-based databases that were specifically tailored to the task and mostly about connection, how you crawl the data. Then in the 70s, the relational database started to appear. It's not like you know it today. It's not the SQL-based database, but the term was coined, and people started to build relational database, which meaning generic databases that are not tailored specific to a specific problem. And obviously, in the 80s and early 90s, the SQL was defined, and people started to use SQL, and it became kind of the standard de facto when you're talking about database. And when someone is talking about database, usually they imagine SQL or relational database, and that was the dominated technology from the 90s probably until today, even though NoSQL is pretty strong and making a lot of noise, but that's still the dominated technology everywhere. And in the 90s, starting with the object-oriented data programming and the fact that people started to do object-oriented programming, people started to imagine that they need to have an object-oriented database. So they asked for a way to store object in the database and to store more complex data than relational, than breaking the data into lines and tables. And you started to see object-oriented databases, XML databases that started to model the data as a more hierarchical data. And in the 2000s, the NoSQL agenda started, and everyone are doing NoSQL because it started from kind of relational is not scalable, is not matching my need. I need another solution. I need something that is more scalable, easier to scale, is not requiring joins and tables. And the NoSQL started to flourish from there and till today, obviously. But kind of the evolution is a myth, as you can see, right? If you look today at the way people are building their applications in the area of NoSQL, so there is this edge of specialization. So now you're starting to see different models, different databases. Obviously, you still see the relational database controlling the market, and most of the applications are modeled using relational database because it's easy and most of the people know how to use it. But you started to see, obviously, document-based databases like Cassandra, Mongo, Couchbase, and many others. And that kind of triggered the NoSQL boom. And then you start to see more simpler databases, like key value databases, that are not complex as document database, but allows you to do very specific tasks, key value tasks that you don't need this complex object style or document style storage. From there, you started to see more spatial databases, like graph databases. In the last 5 years, you see a real boom in this arena of databases, and many graph databases started to appear. Obviously, Neo4j made the biggest boom and the known database, but everyone are doing graph database because they realize that document database or key value database or relational database are not solving the issue about how to crawl the data, how to find paths in the data, how to do social data, or stuff like that. And then you see a more specialized databases that started to appear, the TimeSeries. You see it in the last 3 years after the IoT kind of buzz grew, and like everyone are doing IoT and smart homes and sensors, and data is everywhere. But most of the data is numerical, so I can do a more specific database, a TimeSeries database that know how to handle numerical data, aggregate numerical data, handle it faster, and ingest millions and millions of transactions a second, because the database is aware that the data is very, very simple. And obviously, there is another database that flourished in the last couple of years, is the search database. Is the, you probably heard about Elasticsearch and Solar. And again, with the internet, with the needs to query the data, Elasticsearch obviously boomed with Logstash and Kibana and all this stuff, which allows you to do a very specific task, which is searching data. It's not as good as the other document databases in storing a lot of data fast, but it is very, very good in searching the data, free text search, multi-index, and stuff like that. So as you can see, the market of database is very fragmented. Like as DB engines show, these are the different databases that DB engines are covering. And you can see that there are many, many different models, and even models that I didn't cover before, showing here, including some RDF, which is a very specific model that allows you to store triples, which is almost like a graph. And you have even more specific databases that are for XML that still survive. And XML has some kind of another wave these days. And object-oriented database. So there are many, many models, each one of them specifically for a specific task. But still, the market is being controlled by the relational database, which is kind of the generic solution. But it's kind of the generic solution that is not good in any other task. But if you don't have a very specific requirement or very low latency requirement, you're probably going to go with the relational database. But that's not what we want to deal here. We want to deal with that, with all the rest. Like, we want to make sure that you'll get the best latency, the low latency solution for every task. And you shouldn't compromise about working with the relational database just because it solves all the tasks, but you compromise on performance. So let's look, for example, on a simple query that you might want to ask. You might want to ask, please find the restaurants my friends recommended within 3 miles radius. As you can see, there are two parts to the question: what your friends recommended, and the second part is, what are the restaurants that in the radius of 3 miles for me? And for that, I'm probably going to need a non-binary database. I'm probably going to need some geolocation database, and I'm going to need some graph database. So that's probably going to be the recommended solution that if you're going with, I don't know, with AWS or any of the cloud vendors that do not provide multi-model database, they probably recommend you this kind of a solution. Meaning, take a graph database and take Redis as a geolocation database, take some Lambda that will synchronize between the two databases. So whenever there is a new restaurant coming in, you might need to synchronize between these two. And whenever a new recommendation coming in, you need to update this one. And whenever you create a database and you want to find all the restaurants that your friends recommended within the 3 miles radius, you need to create the graph and then take the results, go back to Redis, find which one are in the 3 miles radius, and return the result. Obviously, latency is added here. Like, you have a couple of hops here, and you are wasting time on latency. But what if you want to make a more complex, or probably what people usually want to ask, like, I want to find this restaurant, but please sort them by, I don't know, by load. I don't want to go into this restaurant and find out that I need to stand in line for 2 hours. So please find me the restaurants in my 3 miles radius that are not too loaded in this hour. So I'm probably going to add another database. I'm probably going to add some TimeSeries database into the picture. And I'm going to need to synchronize with this third one. And the more requirements I'm getting from my organization is getting, the more databases or the more infrastructure I need to introduce. Or maybe I want a falafel because that's what I'm usually eating. So I need to find a falafel. So to find a falafel, I'm probably going to need some free text search database, right? So I'm probably going to introduce an Elasticsearch. So now I have 4 databases that I need to synchronize between them using some, in this case, a Lambda, but any application that I want. and use this application to retrieve and synchronize between all different three databases. And what happens if one of them is disconnected? Does it mean that I cannot answer the question anymore? They have different scaling mechanism, they have different failover mechanism, and everything becomes much more complex this way. And that's not an architecture that I invented. This is the recommended architecture that Amazon is recommending. This is how they recommend to answer this specific query. You need some Elasticsearch, Elasticache, you need some Neptune, and another Elasticache, and you use all of them together to get this answer. And when you're looking at that, it seems like you're wasting a lot of energy in synchronizing all the different databases, deploying all these different databases, managing all these databases, paying for the different databases, different pricing for different databases, while you only want to do is asking in my eye, a very simple question. So, and that's not unique to this specific question or this specific application of finding me a falafel in my 3 miles radius. That is very common to almost most of the applications today. You usually need to mix and match different databases to get your task. You need to mix and match like key value with document or with RDBMS, or you might need to do some caching. And usually your application is becoming more and more complex. The more requirements you get, the more infrastructure you're starting to introduce. And it's pretty easy to do it in the cloud time when you just need to click and deploy a new database, but it's kind of lying to yourself because you still have another database that you need to make sure that is synchronized, that you can connect to each one of them, and you can make sure that the result is consistent. And you need to explain that to every developer that is coming. Why do you need this big spaghetti and what everything is doing? So as I said, it's increased application complexity. It costs more, and makes your life usually harder, even though that seems like the recommended solution from the cloud vendor. So, as presented in the keynote, we see this multi-model solution, or the way to tackle this problem, in 3 different layers. If what you're looking at is just reducing the amount of vendor that you are using, but still want to work with the different models and synchronize between them by yourself, you can go with Redis and just deploy different models. You still need to synchronize between the different models, but you are dealing only with Redis. You're not dealing with different databases, different vendors, different scaling mechanisms. But you don't need to change your application too much. You're still working with isolated different models, but with a single vendor. So the switch from this one to this architecture is pretty simple, because you're still seeing a graph database, a TimeSeries database, a key value database, and so on. But you might want to go another step further. And you might want to introduce some kind of a message broker, some ways so when you ingest the data to Redis, you don't need to deal with the different database. You don't need to synchronize between the different database. Or whoever introducing new data to Redis does not need to deal with that. You just push the data into this message broker, and the message broker or the bus is synchronizing the different models. The second step that we see as an option is you can still work with these different APIs. Like you might want to, your application might need a graph, your application might need a search, your application might need a key value. Again, depends on your application. But you don't want to synchronize between the two different. You don't want to synchronize between graph and search. You don't want to, whenever you introduce a new store to your database, you don't want to push it into the graph database and push it into the search database. And that's what we introduced on, in the keynote. We call it a multi-model or inter-model communication, meaning this time we can make one module or one model work with the other model behind the scene. So the application is only working with a specific API, with a graph API, but it's still getting the service of a search. So you're always working with a single API graph. You push data to the graph, you read data from the graph, but you can mix and match search in it. Same thing with TimeSeries or with JSON. So you can use TimeSeries events, you can push TimeSeries, you can label it, and you can utilize the search behind the scene, the Redis search behind the scene, to find all these TimeSeries and aggregate the coordinate. And soon we're gonna release this one too. Like you're gonna have a Redis JSON database that you can store JSON in, but you can still use Redis search behind the scene to query this JSON. And in a sense, you will be able to get a free text search on a document database. But I think the most interesting piece is, what if you don't know in advance? You don't know in advance what your organization want to need. You don't know in advance if your organization is going to grow and will need a search or a graph. And you usually start with a small solution, and you just store the data and retrieve the data in a simple way. So let's look at a real-life example of how an organization can grow with us. So, sorry, not this one. This one is a fake. Let's look at the real one, the governor. So I'll take this movie and then we'll grow from here with this example. So whoever knows this movie, meaning that probably was born before 90s, so it's great. So not too many, I guess. So if you remember the movie, the cast started with 3 different characters. There were Douglas Quaid, Schwarzenegger obviously, and his wife, Sharon Stone, and some other girl that we don't know who is she, Melina, so we'll call her Melina because I don't know her last name. And we want to store it into Redis. So if you are a producer and you have a movie and you need to store all the cast so we can play with it later, so you're probably going to use Redis for that. Let's start the Redis. So you have a Redis. And the first thing, let's skip this line, but I'll talk about it later. I'm introducing this module Redis gear. And I'm just storing all this, the cast, right? I'm just doing edge set, Marsman 100, Douglas Quaid, Laurie Quaid, and so on, Melina. So that's a simple Redis use case. But what happens if my director is coming and say, I need a search engine for that. I cannot work with this because I can't really search the data. The data is stored. You can add information about it, but I can't really search. I need to search. The cast is so big. There are 3 characters, and I can't really find anyone, so I need to search for it. So I want to have support for QU, for example, for search. So in that case, it's pretty easy. You don't need to restart your database. You don't need to do anything else. You just need to introduce Redis search on the fly without restarting the database and define the schema for Redis search. So in that case, the schema is very, very simple. You just have 2 fields, a name and a last name, and they're both text. And what left to do is to make sure that these 2 modules will talk with each other. So for that, we introduce Redis gears, and it allows you to define the mechanism or what to do with the data and how the data can translate into other data and stored into Redis, and what to do and how to react on the data when a new data is introduced to Redis. So I'm just sending these 2 Redis gear commands. These are very simple Redis Python code. You don't see it here nice because it's a shell, but let me show you. These are 2 simple, you can see it here. 2 simple Redis gear commands. The first one is saying, take all the hashes from and put them as a marsman, like in the index marsman. And the second one say, whenever there is a new key registered, when there is a new key was updated, a new hash was updated, update the search engine too. And that's it. So let's go there and see if it's working. So you see it's working. I can do search by QU, and I'm getting Laurie and Douglas. Both are last name started with QU. So that was nice. Let's hope it's working for more than that. So the cast was growing, and new characters introduced. Harry, the best friend of Douglas, Bob McLean, and Vilos Cohagen. So let's just make sure that it's really working, like the notification is really working. So let's write these 3 new characters into the database. I'm still using Redis simple API, edge set. I'm not using Redis search. I'm not using Redis graph. I don't need to learn a new API where I'm introducing data. I don't need to synchronize between the different databases. I'm keep working with Redis. Behind the scene, Gills will synchronize the data and make sure that everything is synchronized between the different models. So if I'm searching for MCC, I see that I'm getting Bob McLean. So it's working. So so Redis gear is following all the hashes and dynamically synchronize Redis search. Let's go back to the slides. So what about relationship? So we know that Douglas is married to Lori. So my director just asked me to add some, to be able to query the relationship and find who is married to who, what are the relationships in this movie. So obviously the right solution for that, I'm going to run and buy a graph database. But in that case, I might not need to do that. I'm just going to introduce another model to the picture, which is Redis graph. Again, I'm not restarting the database. I'm not reloading the data. I'm not redefining the data. The data is still hashes. The basic data set is hash. And all I need to do now is to create a relation. In that case, I'm creating a relation like I'm doing an edge set. Again, I'm working with Redis API. I'm not changing the way I'm doing. And I just added a new field to this hash, which is relation. And I'm saying 101 is in relation with 100. So Lori is in relation with Douglas. And again, I'm doing the magic with gears. I'm synchronizing the data between the hash and graph. So now what I'm telling gears to do behind the scene is whenever you see a hash updated, take the relation, create a relation in graph. And if you see a relation, remove it. And if you see, and just for the beginning, start with scanning all the hashes. And if you see a relation in one of the hashes, create a graph out of that. Again, we can switch into the code if you want to see it in a more clear way. So you see, this is the way you're doing it with gears. You just need to tell it this part. And this one is translating all the hashes into, this one is translating all the hashes into a relation database or graph database. Let's see if it's working. If it's working, tell me because I can't hear anything. It's not working? No, you're not seeing. Oh, sorry. You couldn't hear it, but what you were supposed to hear is that. Consider it as divorce, right? So we might need to disconnect the relation. So, it's not stopping. So how do you do it with Redis graph? Oh, I forgot to show that it's really working. So after I introduce the relation, you see that I can query the relation with Redis graph, and I'm seeing that Lori is in relation with Douglas, and I might create another relation. For example, I saw that he has a friend, and we can see that now there are 2 relations. Harry is a friend of Douglas, and Lori is a friend of Douglas, is wife of Douglas, and we saw before that there was a bad divorce between, a bad separation between Lori and Douglas. So I can just delete this relation from the edge set. And if I'll query again the graph, I can see that the only relation kept in the database is Harry and Douglas. So yeah, it was a bad divorce. Let's go back to the slides. Sorry for that. Oh, sorry. So I might need some biometrics, right? If you remember the movie, Schwarzenegger had a bad time when he was injected out of the without oxygen to Mars, and I might need to monitor his biometrics information and his heartbeat, and I want to make sure that he's alive because he's on Mars. But we saw that he had a bad time. So for that, I'm probably going to introduce TimeSeries. Again, I don't need to restart my database. I have another module now introduced into the database called TimeSeries. And this database allows you to monitor numerical data. But now all I need to do, to define a way how to monitor the data. So for that, I'll introduce a new field to the hash, which is the heartbeat. And whenever this field is going to be changed, a new record will be created dynamically in the time series. So again, I need to take gears for that. I'll take gears. I'll create gears register. I'll register another event on gears that will say, whenever you see this field change, the heartbeat field change, introduce a new event into the time series. And then I can start following the history of this field and get more information. So let's load some data. So as we saw, his heartbeat started to raise because he didn't get enough oxygen, and it continued to raise and continued to raise, and we can wait with that. But if you remember the movie, after about a minute without oxygen and in this hush acclaim of Mars, the mountain blew up and he got all this oxygen and his heartbeat got down and everything was okay. So, so we just experienced a heartbeat pop. So I can use now Redis time series to query this data. And I can look at the data and see what's the average heartbeat per 5 seconds, for example. So we can see that every 5 seconds the heartbeat raised and then decreased. And I didn't do anything special, but that is not Redis-like. I kept on doing age set, age set, age set, age set, updated the value. But in the background, Redis gears followed this data and created new events in Redis time series. So now I got this, I think, very nice application, very nice database. I'm working with Redis. I have a multi-model solution. I don't need to introduce different vendor, different technologies. And everything is done automatically behind the scenes. So I don't need to synchronize, between the different database. And I don't need to query different vendors. So where can you find this example? So Redis gears, as you probably saw in the keynote, was introduced today. So we have a repo for that, and we have a repo of example that we are, an organization called Redis gears that we are starting to accumulate examples there and use cases. So this is one of the examples that you can find there, like how you can build step by step the multi-model database. If you want to learn more about the different modules, so we're going to have like a set of different sessions during the next 2 days. We're going to start with gears next hour with Meir, who is the creator of gears. Then we'll have Redis AI. You're going to see me again there with Luca. And that's the other module. I didn't present Redis AI here, but you can see it there. Time series, obviously, Dan is going to show it tomorrow. You're going to see more into details how it looks and how to work with that. And Redis graph. There was one presentation today, and there is another presentation tomorrow going deep into the details, how the queries are running behind the scene, how you can optimize the query. And last, Redis search, which is not new, but there will be a new session tomorrow about how you can use it and synchronize it between sites, active between different sites globally. It's also presented on the keynotes. Thank you. If you have any questions, we have a lot of time. Feel free to ask. Over there.
Test.
We
Okay,
can hear you.
sorry, raise your hand again because I need to bring you the microphone. Okay, we have 2 questions. All right. Let's go with the lady first, then I'll get to you.
So how does the synchronization happens between different models?
So as I showed before.
As in backend, like as a user, I might don't have to handle it, but how does Redis do it? And how do I know when it will be available?
Oh, when it's going to be available, it's going to be available. Yeah, I showed you. So I showed some codes here, but snippets. But you can see here that we are using Redis gear for that. You see RG PyExecute. So what you're doing here behind the scene is you're sending gears a Python code and define how you are, what is the sequence of operation that you want to do with the data to make it synchronized with the other modules. It doesn't have to be synchronized with other modules. You can just return the data if you want. In my case, I use it to synchronize, but the gills, or if you want to hear more about gills, just stay to the next session, by the way, with Meir. But it's, the preview is available. You can go to the website. It's called redisgills.io. You can go there. You can start play with it. There is a Docker there. You can download it. You can install it. It's workable. It's not GA yet. It's in a beta phase, but I think you can start doing very nice things with it.
So what happens when you have a failure where you've updated part of the system, especially if it's a cluster or some form, where some of the database, some of the model has been updated, but maybe the graph hasn't been?
Okay. So as I said, the nice thing is that we try to make sure that the partition schema is the same. So everything is done locally. So when a hash is updated locally, and the graph and the time series and the search are all on the same shard. So it's not cross, so you don't need to update it cross shard. So usually when an update occurs, it occurs locally, okay? So there is no cross shard transaction distributed data. I'm not saying that you cannot do that, but you need to try to go this way, like making it locally. In this way, all the updates are local, the latency is almost zero, and you won't get partial updates, because if the shard goes down, all the updates are going down, right? With the updates.
So is that should or?
1 second.
Is that should or certain that you will never get a partial update?
It depends how defined. This is not this is a solution. This is not a product, right? What I showed you here is how to build it yourself, right? Using Redis gears. So if you need to distribute the data, then you'll cause distributed transaction in a way, right? But if you don't need to distribute data, if you can make sure that the time series and the hash that is related to it will sit on, you need to make sure that they're going to sit on the same shard. And the search, right, the data that indexed the same hash will sit on the same shard, then everything will be local, sorry. Okay. If it's not, it doesn't answer your question.
Well, if it's within local, there's no way to get a partial update.
There is a way. No, there's no way, because in a sense, because if the shards survive, then all the updates will happen. If the shards die, then all the updates are not there anymore because the shard died, right?
Okay.
I think what they're getting at is the same question I'm kind of getting at is, how do you know when this information has been updated into the database? How do you know, and what is the big O of this calculation here? Because I noticed you were dealing with 3x3 data sets, and it was taking 0.3 microseconds. So are we talking about a big O of n squared here, or are we talking about a big O of n log n? I mean, you're talking about parsing through. When you make one update, you have to kind of parse through the whole list. So
it depends. It depends. It depends. What are you talking about? The time series? What are you talking about? Or the update themselves?
Yeah, the update itself.
Oh, the update itself. So as you saw before, there are two phases to this update. So there's a phase when you introduce the new model. So in that case, yeah, you pay an O of n because you need to scan the data and make sure that all the data that is relevant to the graph or to the time series or to the search will be indexed as a graph or a time series. But that's one time when you introduce the new model. But then when there is a new update, it catches the key update. So on update, we react on it and update the specific model. So it's off one in a sense, right? What are you showing me? So see, this is a run. These are one time. You see, these are run. If I'll go there, you see that's a register. So whenever one of the keys of Marsman, okay, you get a key space notification from Redis. On every update, you can register for key space notification. If you're writing a module, a Redis module, you get a key space notification on every update, and then you react on it. So the only thing that you need to verify is that it's relevant for my action. In my case, I only wanted to see hashes that start with Marsman. Okay, and then I react on it. What I'm doing updating the graph, updating the search, updating the time series. But these are all O of 1 operations. Big but? I can't hear you, sorry.
Sorry for taking so much time on this, but if you're looking for a match inside of your database,
No, it's not a match, it's on event. So whenever there is an update, like when you are doing an edge set, Redis notify the gills on this update or this specific update, saying, this key was updated, do you want to do something with that?
sure, that's the request.
No,
Then
that's the register. You see
But
the
then
register?
then there's the match that has to occur, right? You have to look
Which
for the
match?
match of Marsman.
No, but that's gone, this one, this part. But this one is done using the Graph API, which is already indexed and know how to do it efficiently. Okay?
Okay, any other question? Please raise your hand. Okay.
Over there.
Oh,
and over
okay,
there.
yeah.
Question about what is open source and what's licensed, etc.
So I don't know if you follow the licensing.
Yes, I do.
You did.
I did.
So all of these modules are Russell license, meaning ready source available license, with this limitation, meaning that unless you are building your own graph database or your own TimeSeries database or something, or provide such a service, you can use it for free as an open source, change it, update it, fork it, whatever. The minute you want to start selling it as your own product, not part of your product, but as your own product, like you are selling a database or a database service, then you are not covered by this license.
But if I have products in specific domain area which uses this, it's fine.
Enjoy.
Okay, any more questions? Any more hands? Okay, I see no hands. I would like to add one last thing then. About, for the gentleman that was asking about consistency and persistence. Correct me if I'm wrong, guy, but so this is a demo. But if instead of piggybacking on hashes, you were using streams, that's another way you can ensure that you don't lose the history of your updates. And you can still use Redis transactions when doing these things. So you can still mix and match all the Redis operations that you know to produce the result that you want.
Yeah, but you kind of revealed the secret of tomorrow keynote.
Oh. Fuck. Okay, then
Thank you.
Thank you, Guy.
Thank you very much.